Good morning, good afternoon, good evening, depending on where you are in the world. I'm going to be talking to you today about the overlap of smart systems and energy systems. We're all concentrating on carbon reduction. It's very much in vogue these days. And one of the things that is very important in carbon reduction is energy systems. And you might think that if you are an intelligent systems person into neural networks and other deep learning, all that sort of thing, you don't have a place in energy systems. But I think you're wrong. So just before we do that, a few words about KES, because I was privileged to be the person that started KES with Lakshmi Jain, and over 20 odd years we've grown that into a community of several thousand people, and for those that don't know, we have an international conference series on various aspects of intelligent systems, which next year is going to be in June on the island of Rhodes in Greece, somewhere warm and sunny. We have a September conference, which is really where KES started from. It started with the Broad Spectrum Intelligent Systems Conference each September. In 2022, that's going to be in Verona in Italy. And then we branched out because although I started as an electronic engineer, I moved into software engineering and then into renewable energy and sustainable energy systems. So I started a conference on sustainability and energy in buildings, and we built that up and then added to it a conference on sustainable design and manufacturing. So we got these two sustainability conferences. We have various times also run other conferences on things like knowledge transfer, technology transfer, innovation, because that's something that I was doing when I was at the University of Brighton, and other conference areas. We have a journal, the International Journal of Knowledge-Based and Intelligent Engineering Systems, getting a lot of interest at the moment because it's indexed in Scopus, EI, and ESCI, Emerging Sources Citation Index. I personally, along with Professor Lakshmi Jain and John Littlewood, we edit a book series on advances in sustainability, science and technology, and Lakshmi and I edit a book series on smart innovation systems and technologies, both with Springer. And I get involved in various, I don't do a tremendous amount, which is useful these days. I kind of moved from research into managing and making money, but I've kept my hand in with research, and I do get involved with various collaborative research projects. I'm involved with a couple of PhD students down at Cardiff Met University, and I do get involved, as I say, with energy projects if they're taking place somewhere warm and sunny. So we're all, as I said before, very focused towards carbon reduction because it's an incredibly important topic in terms of ensuring that the planet remains habitable, really. Now, each country has its own individual targets. We know about the COP26 conference that's just been. Just looking briefly at the UK targets and trends, which are typical of other countries as well. The UK has a legal obligation to become net carbon zero by 2050. And a plan to phase out the sale of new petrol and diesel cars and vans by 2030. A lot of houses in the UK are heated by gas, and there is an aspiration to end the gas supply to new houses sometime in the 2020s, which presumably means by 2029, 2030, to phase out the installation of new gas boilers by 2025 to 2035, And this is quite important in terms of what we're going to be talking about today, because the intention is to replace those with heat pumps of various sorts. The UK launched its 10-point plan for a green industrial revolution in November 2020, and has just produced its heat and building strategy in October 2021. And without going into those documents in huge detail, the takeaways from the building strategy, heat and building strategy, were building energy performance, which has always been important, heat pumps, and hydrogen. So they're kind of the three key things from that strategy document. And one thing which has been apparent for 10 to 20 years is the rapid drive to electrifying the power value chain and making electric power the predominant form of energy. So in terms of the electric power system, that's being driven by economic developments in a couple of areas. So the price of PV has come down astonishingly over the past 20 years, and the cost of other renewables is coming down as well. PV electricity is very cheap in the middle of the day if you want it, but it's extremely expensive at midnight because you can't get it. So PV is useful in combination with electrical storage, primarily by batteries, although through other sources as well. And then, as I said before, the third modern technology, it's been known about for quite some time, but being developed very much in the recent past, is this idea of heat pumps, and we'll talk a bit more about heat pumps a bit later. So you've got the renewable technologies, the energy technologies on the one side, but equally important, you've got the enabling technologies on the other side, which are the electronic technologies. So at one time, the energy distribution system was a dumb system without much in the way of sensors. There were meters that people looked at, but there weren't huge numbers of sensors. Now we have the capability to instrument the system at various points using networked sensors and what's being called the Internet of Things. That produces huge amounts of data, and we can get useful information from that data using artificial intelligence, machine learning, all the big data technologies, data analysis technologies, statistical technologies, and so on, to get meaning from that. And something which is often forgotten is that all of those things really are only possible because we have high power computing. I did my PhD back in the 1990s, worked with neural networks, and I was working with an IBM PC with a clock speed of about 10 megahertz, and everything was done on that IBM PC, which really limited what you could do in terms of the in terms of the algorithms and so on, because you didn't have the computation power. So this high power computation is extremely important, an extremely important part of the other things. So in terms of developments of the energy system, we've got a whole load of things that we didn't have before that we want to hang onto our energy networks. We've got various types of renewables, photovoltaics, solar thermal. We've got combined heat and power systems, heat pumps, biodigestibles and sewage being turned into energy or turned into gas via biodigesters, wind turbines, and various types of electrical storage, batteries, hydro storage, pump storage, all kinds of things like that. So we've got a whole array of technologies that we want to put onto our energy system. Interestingly, we still have a place for fossil fuels, gas and oil and so on, because they are dispatchable. We can turn them on, we can turn them off. Take some time to crank up a gas-fired power station, but if we know that we need it, we can turn it on. A lot of primary renewable energy systems are non-dispatchable, and that's quite an important point. We don't quite know how much wind energy there's going to be this year. The amount of wind that's been blowing has been relatively low, and the output from wind turbines around the UK and wind farms has been relatively low, and that's relatively unpredictable using current technologies. Although there are ways that we can approach that. The weather in the UK and across much of the world is remarkably fickle, and you don't know quite when the sun is going to be shining and when it's not. So photovoltaics, you can make estimates about how much power you're going to get from it, but you can't exactly know, because those are non-dispatchable energy resources. So at one time, the energy distribution system was in the form of centralized power stations linked via transformers over long wires to where the power was needed. So you'd have your power station, coal-fired, gas-fired, whatever, power distributed over long distances by 400 kV high voltage, extra high voltage distribution lines, transformed down to 132 kV, where it's used for heavy industry, transformed down again for light industry, and then down into a lower voltage for towns, and ultimately to 230 volts or 110, 120 volts in the States and some other places for houses, farms, villages, and so on. So you ended up with kind of a hierarchical system where the power is generated and the wires got progressively kind of thinner in terms of their carrying capacity until you get down to the far end. Now you've got a bit of a problem, because if you think about what we're trying to do now, we're trying to take wind turbines, photovoltaics, all kinds of things which generate electricity, and we're trying to put that power in down at this end here, whereas the system's actually designed for the power to be injected up at this end here. So the kind of centralized generation system with long distribution cables to the users isn't really suitable for modern trends. And you know, the modern trend is towards distributed energy resources. So one thing that's being looked at is the idea of a microgrid, where you try and decompose the national grid into small areas, small self-contained subsections of electrical grid. And that enables you to use energy generated close to the user. So the PV, which is built up, which is mounted on the roofs of buildings and so on, can be used in those buildings and shared between buildings when some buildings have a surplus and others have a dearth, a lack of energy. So your microgrids, this kind of structure like this, we have our offices, housing, community buildings, so on, some of which have building integrated PV. We might have wind turbines, although there are problems with those in urban areas. We certainly got PV in terms of, as I say, building integrated PV, but also PV farms. And then we have electrical vehicle charging. We might have CHP. We might have heat pumps. We might have storage. But we have all of this in a kind of a relatively self-contained area. We have the ability to, we have a grid connection, so we have the ability to import and export power. And one important thing these days is the importance of resilience and having things which are self-contained. So if there is a disaster, some sort of problem, a particular area might be able to keep going, whereas the rest of the system doesn't. So with a microgrid, we have a national grid connection, but there is the potential for disconnecting from the national grid. So if the national grid goes down, our microgrid can continue to operate. And where these are applied, they're often used in places like, hospitals and military bases, areas where it's important that the system doesn't go down if the grid goes down. The problem that you've got with this kind of area, this kind of system, is the heavy reliance on non-dispatchable resources such as PV, wind turbines, and so on. You may need backup generators. You may need other dispatchable sources for times when the renewables are not available. And you have got quite a complicated control problem. You need to try and predict when renewable energy sources are going to be there, when the PV electricity is going to be available, and so on, and when you might need backups. You need to balance generation from PV and wind turbines against storage. How much do you store? How much do you use? When do you take power from the grid and store it against future use? And how do you integrate all of these other complex resources? So it's quite a complex control problem there, and potential for intelligent systems. So this is the kind of problem that you've got. On this side, we've got graphs showing demand for electricity. And the electricity utilities and generation companies have records going back over probably 50 years, something like that. So they have got a reasonably good idea about how much electricity is going to be required from time to time. But on this side, we have availability of renewable generated electricity from wind power. And this is much less predictable. So in a system which is mainly fed by, where the electricity provision is mainly from renewables, you have kind of this sort of problem here, that at times you have a surplus of power, which is represented by green on this graph, and at times you have a deficit of power, and you need your storage to ensure that the generated electricity during these green times compensate for the lack of power during those red times. And that's quite a complicated prediction problem, but one that intelligent systems are being applied to. So in order for us to make these kind of predictions, we need, as I said before, network centers. We need to be able to measure energy consumption at various points. We need to be able to do environmental measurements, temperature, wind speed, solar. We need to communicate via wired or high-speed wireless networks. And we need to provide information for the human user to be able to make decisions about these things. And the place where artificial intelligence, renewable energy, artificial intelligence, machine learning, and these other technologies have a place is to look at that data, analyze it, and try and forecast future demand. We can already do, some of that, but renewable energy availability is quite a tough problem, and one where artificial intelligence is being applied, but there is still, there is still the possibilities there of other projects kind of in that area. So we need to enable comprehensive, accurate match to be made between the energy available and user demand. How do we do that? lot of interesting things going on with cloud supercomputing. You will know if you're into machine learning and that kind of thing. The current technology for deep learning often involves you uploading your data to the cloud, where Mr. Google will let you use his Cray supercomputers for free or for a reasonable charge, and you can generate your neural network model, which is then downloaded and used. When you go to the inference phase, the operation phase, you can either again upload data to Mr. Google and use their computers to draw conclusions, or increasingly there's interest in edge computing, various inference accelerators. Jets and nanos are really interesting little piece of kit that you can have on your desk and will enable you to do the inference phase of neural networks on your desktop instead of having to pipe things up to the cloud. There are huge questions about this idea of pumping things up to the cloud for analysis in terms of data security and in terms of the delays, latency, unpredictability of latency and delays and so on. But really interesting kind of field, and one which is absolutely applicable to the energy field. So if we go back to our microgrid, and if we add to all of our renewable energies, our distributed energy resources, if we add to that Internet of Things, network sensors, and we add artificial intelligence, machine learning, then we got what's increasingly being called the smart grid. So let's say we want to try and take our intelligent systems. What can we do with them? Well, something IBM's doing. Excuse me. Something that IBM's doing, the Deep Thunder project. They're able, they claim, to produce what they call hyper-local weather forecasts. Now, weather forecasts in the UK, sometimes they are accurate, sometimes they're not, but IBM claims to be able to give you a weather forecast for a specific location within a city or within the country. And they claim a couple of blocks radius. Now, that's quite useful because if you've got PV on your building, then it gives you some information about whether or how much electricity you're going to be able to generate from that PV. Because you've got a weather forecast, you know whether it's going to be cloudy, you can estimate from that the insolation, the energy coming from the sun, and therefore the amount of energy, which is the amount of electricity which is generated. Again, it's still something which is done via supercomputers in the cloud, not something that you can have operating on your desk, but an interesting indication about the way that things are advancing. So a few things about AI. There are various intelligent system paradigms, and where do they fit? Well, if we're talking about energy availability and demand forecasting, learning building thermal models and so on, then probably we're talking about neural networks, potentially deep learning neural networks. If we're talking about control and coordination, matching supply to demand, buying, selling, because there's a whole lot of things around energy trading, then possibly we're talking neural networks, but also fuzzy and neuro-fuzzy systems, genetic optimization, and so on. If we're talking energy trading, wholesale markets, peer-to-peer trading, then there's a lot of work being done on agent and multi-agent systems for that kind of thing, neural networks as well. And there's a lot of older work being applied to energy systems in terms of condition monitoring and prediction of failure, which I did some work on quite some time ago, looking at wind turbine bearings, breakdown of cable dielectrics, monitoring of PV panels, where again, neural networks can be useful, neuro-fuzzy systems. I was working in this area many years ago, and it's all come back and being used again now. So that's really just a snapshot of some of the ways in which intelligent systems can be applied in the energy field. So some examples. We've been talking about microgrids. This is a microgrid, a practical microgrid, which is in operation. This is in Brooklyn, in New York. The Marcus Garvey Village is a social housing estate. It's quite, a number of buildings. There are 21 rooftops, 21 buildings, and the generation capability of the microgrid is that they have photovoltaics on top of the majority of these rooftops. The housing estate was built in the 1970s and refurbished in 2017 and made of 625 housing units, 32 low-rise buildings built as a neighborhood over 10 city blocks. So, it's quite a substantial sort of thing. So on there, you've got 480 kilowatts of PV. You've got a 400 kilowatt natural gas powered fuel cell. And you've got a 300 kilowatt hour lithium ion battery pack. And also a national grid connection, which gives you the ability to export and import power from the grid and islanding capability for self-sufficiency. So this photo here actually shows the storage facility. It's built in a shipping container which sits in a car park. So it's not absolutely huge, and the fuel cells are in there as well. So PV generates 563 megawatt hours annually and powers 80 homes. Huge CO2 offset and a huge reduction in power bills. One thing which is often not thought about is that this kind of system has the obvious benefits through reduction of power through generation of solar electricity, but it also produced savings because if they didn't have the microgrid there, they would need to build a new substation, which was estimated as costing $1,000 million. Didn't need to build that, and hence saved that amount of money indirectly. The system's also useful because the power utility, Con Ed, Consolidated Edison, I think that is, buys power from the microgrid when it needs to and is available to sell it back when the microgrid's in deficit. And you have this idea of resilience during a storm. A few years ago, the rest of New York, the power was lost, the grid went down, but the Marcus Garvey estate, the lights stayed on, as they say. They continued to operate because they had their own local system. So let's just talk a little bit about where we use energy. And this is a slide showing energy consumption in the EU. Space heating, about 64%, and water heating, about 14.8%. That's quite interesting. Heat and water in the UK, in UK homes, is responsible for about 13% of the UK's carbon emissions and about 79% of energy requirements, according to the UK Climate Change Committee. So domestic energy use for heating and hot water is incredibly important. So, as I said before, the UK government has an aspiration to eliminate gas boilers. Many houses have gas-fired boilers, and the intention is to eliminate those from UK homes. And what's it going to replace them with? Well, they're talking about replacing them with this heat pump technology, which basically is a means of taking heat from where you have it, taking low-grade heat, putting it somewhere else, but also raising the temperature. So you might be able to you can take outside air, which might be, say, at 10 degrees, you take the heat out of that air, so the temperature is reduced to 5 degrees, and then you take that 5 degrees of heat and you transfer it into a building where you use it to increase the temperature of the output of the system to provide heat for the building. This is not magic. This is not contravening the second law of thermodynamics, because you're not actually generating heat. You'll take it from one place, sending it to somewhere else. Not going to spend a huge amount of time talking about this technology, but that basically is the nub of it. Where do you get the heat from? Well, you can either get it from air. So this is an air source heat pump, which looks like an air conditioning unit. Well, hey, an air conditioning unit is a heat pump. But the way that it's being used here is to take heat from the outside, put it inside, although they can be reversible, so they can be turned back into, they can be used in air conditioning mode for cooling. You may get the heat out of the ground via buried coils, or coils buried in the ground, which have a circulating fluid, which take the heat out of the ground, and the ground is at a relatively constant temperature, unlike the air, where the temperature varies considerably. Or you can take the heat out of water by using water source heat pumps. So this technology, huge amount of interest, huge amount of research has gone into heat pump technology in the past 10 years or so, although the technology itself is much, much older than that. But efforts have gone into improving efficiency and particularly increasing the temperature of the output side. So with heat pumps, you have something called the coefficient of performance, which indicates how many kilowatts of energy output you get for each kilowatt of energy input. So if you have a heat pump with, say, a coefficient of performance of 3, then what that means is that you put 1 kilowatt of electricity in, and what comes out is 3 kilowatts of heat. Now, the coefficient of performance depends very much on the difference between the input temperature and the output temperature. So, for example, if you have a 20-degree difference, so you want to get to 20 degrees output temperature and the input temperature is 0, then your coefficient of performance can be quite high. But if the temperature difference is, say, 60, so the input temperature is 0, it's an air source heat pump, the temperature of the air outside is 0, it's freezing, and you need 60 degrees for your heating system, then the coefficient of performance is likely to be much smaller, kind of 2 or 3 or something like that. And that's the problem. That's the problem with heat pumps, that the air source heat pumps are relatively convenient because you can have a box sitting outside and the input energy is produced by air. But the problem is that when you want heat during the winter, the air is relatively cold. Water source heat pumps or ground source heat pumps have a huge advantage because the subsoil or the water in rivers and canals and so on is relatively warm, relatively constant temperature, but you need to bury the coils in the ground, or for a water source heat pump, you need a river nearby, and we don't all have rivers nearby. So there's the kind of dichotomy of heat pumps. Now, Mitsubishi Electric are doing a lot of work on heat pumps, and they produce a system This is what's called a hydronic system. It's an air source heat pump, but the input energy is a wet system. So the energy from the heat pump is used to heat water, which in turn is then used to heat a building. So this is from Mitsubishi. I use a lot of diagrams used from other people and make no claims that the copyright is my own. So this is a Mitsubishi diagram. So they have their outside unit, their outside box, coupled to a water cylinder inside the building. That's something of a problem for some UK buildings because over the past 20 or 30 years, there's been a move away from cylinders of water in the buildings, and where people have gas boilers, they're combination boilers which take water and raise the temperature to that required for washing or heating or whatever instantaneously. So they don't have tanks. So if you want a system like this, you have to have room for a tank of water. But there you go. So the heat pump heats the water in the tank, and that can then be used for showers and washing, and it can also be used for heating of the house. Now, this is quite interesting because at one time with heat pumps, because you have this relationship between the coefficient of performance and the output water temperature, heat pumps were known for producing output water temperature which was relatively low and suitable maybe for underfloor heating. But Mitsubishi claimed to be able to produce water hot enough to be used in conventional wet central heating systems with radiators. So that's what they say they can do. Now, one of the problems we've got in the UK is that we have a huge housing stock, which is old, which was built at the time when energy standards in building were relatively poor. We're not going to knock those buildings down and replace them anytime soon. They will still be here probably in 2050. So the thermal characteristics of buildings like that are very much different to the thermal characteristics of newer buildings. So older buildings often have a lower level of insulation. We can do a certain amount to improve that with retrofitting, but they will always have a low level of insulation, whereas modern buildings like to have a higher level of insulation. There are differences in terms of the thermal storage characteristics of the buildings, the time constants of the thermal movement, and so on and so forth. So buildings have very much different characteristics. And if you want to optimize the control algorithms, then you need to know those characteristics. So again, something interesting that's been done by Mitsubishi is that they have a control algorithm which looks at the operation of the system over time, heat pump system over time, monitors it using sensors, analyzes it, and produces a model of the thermal characteristics of the building that the system's operating in terms of its heat capacity, its thermal mass, its time constants and time constraints, its heat dissipation characteristics, and so on. And then during the control phase, use is made of those thermal characteristics to optimize the control. So the question kind of with heating systems is always, do you keep the heating system working at a low level all through the day, say, or do you wait until 5 o'clock and then turn it on and produce a lot of heat to try and get the building up to working temperature for when people come in from work at 6 o'clock? Of course, post-COVID, things are changing again because more and more people are working from home and need heating through the day. Now, Mitsubishi don't say whether this control algorithm uses intelligent systems because it's a commercial product. The data that's available on it is relatively small. The amount of data is relatively small, and I haven't read a technical paper on it. I haven't been able to get access to a technical paper on it, but you can see that there's potential there for further research and using neural networks, machine learning, and so on, and other intelligent system paradigms to learn the characteristics of those buildings. Quite an interesting potential project. So what we've seen so far is we've seen microgrids, an electrical network, and we've seen heat pumps, hot water systems, which is like a microgrid for heat. So here's another project. This is a plan for a project in an area of London called Islington. And the plan is, this is called the Green Skies project. The plan is to have a heat network and microgrid in one. So we take an area of buildings. We have roof-mounted photovoltaics for generation. We have other generation sources. We have an electrical store, and we use that electricity. We have a grid connection so that we can import and export power. We obviously use that electricity in the buildings, but we also supplement it with a heat network, kind of a microgrid for hot water. And that microgrid for hot water, well, it's warm water. It's around about 15 or 20 degrees. And where we have households that need heating, we have a heat pump, which pumps heat out of that water, turns it into high temperature heat, which is used for heating the building. But where we have sources of heat, say the data center, which needs cooling, we cool the data center, dump that excess heat into the water loop. Where we have the underground, the metro or the subway, as other people call it, the urban transportation system, that generates excess heat. So we use heat pumps to suck that heat out and store it or put it into the water network. And then we can take heat from the water network and store it in thermal stores. So the idea is that we have a smart energy system, integrates a whole raft of low carbon technologies, heat, power, mobility, the lot, a 2-kilometer ambient pipe loop with hot and cold water storage. It captures the waste heat from offices, data centers, and so on. Use heat pumps to draw heat in and from where it's not required and put it where it is required as well. And an electrical microgrid. And the important thing is to use AI. Important application is to use AI to coordinate electricity demands from the heat pumps and so on. This is quite a big sort of project. 10,000 residents, 3,500 homes, 70 buildings, projected to save 80% carbon emissions. It is a plan, and the design is going to be ready at the end of 10 years, and then we'll see how we will see how it can be applied. So, where have we got to? My kind of conclusions. At one time, electrical distribution systems, generation and distribution systems were purely that. You had the hierarchical situation where you would have power stations often situated next to coal fields because the power stations were often coal-fired, gas power stations situated where there was the availability of gas, and then long cables to the users. That situation is changing because of the availability of distributed energy resources. And energy systems increasingly are both electric power and thermal power, heating, cooling. We need to take an integrated, holistic approach, and it's not really good enough anymore. Much more efficient if we do that, not really good enough just to look at one side or the other. So if we take microgrids, heating and cooling networks, Then we have these integrated heating systems, and there are a number of plans for those around the world. The designs, perforce, need to be bespoke. They're going to be individual designs because it depends on the housing stock that you've got available. It depends on the potential for building mounted photovoltaics, PV farms, wind turbines, the mix of facilities, the mix of energy resources that is possible in the area that you're looking at. The systems are remarkably complex. They need design, they need modeling, and those things are ripe areas for intelligent systems. So there's a huge potential for the use of intelligent systems in these energy systems. Just one more thing, if you're looking for a project, something that I've been interested in, although I haven't managed really to get it off the ground so far. When we're talking resilience, food production is incredibly important. Being able to produce food near where it's consumed gives you an improved measure of resilience. And a lot of food, well, food growth, food production is a big consumer of energy. And an example of that is greenhouse horticulture, glass houses, which have a huge energy demand. And although you wouldn't expect it, some greenhouses almost are microgrids in themselves, have the potential to become microgrids. One system that I was looking at has a 20 megawatt gas turbine energy generation system to produce heat for the greenhouse and electricity for the greenhouse. And again, I think there's a huge potential for integrated energy systems in food production. And a big part of that will be control, modeling, simulation, and intelligent systems. So I think that's me done. And if there's anybody out there listening, then thank you very much for listening. And if there are any questions, then I'll be happy to answer them as far as I'm able.
Thanks, Bob, for a really interesting talk, especially in this climate of renewable energy that is a real focus. I've got questions already come in, but if anyone else wants to ask any questions, there's the Q&A function at the bottom, and we will answer as many questions as we get. But I've had one that's coming from John Littlewood, and he's mentioned for housing association landlords that upgrade an existing dwelling fabric and adding PV and battery storage, are there any challenges to upgrading the existing domestic electrical supply, and what are the solutions from an intelligent systems?
Well, thanks, John. Don't ask me an easy question, will you? Well, there are challenges in terms of the kind of obvious ones. Do you have places which are suitable for putting PV? Interestingly, as the cost of PV comes down, that becomes less of a challenge. The cooperative building, which I think in Manchester, has PV mounted on all surfaces, because even vertical north-facing walls get a certain amount of light. It's scattered light, it's distributed light, but the PV on those surfaces will generate some power. So if you want to make the optimum kind of location is at a particular angle, south-facing, or you may even want to the optimum situation is kind of south-facing at a particular angle to the sun. But mounting in other places becomes cost-effective as the cost of PV comes down. The challenge with batteries is to some extent PV storage as well. It's all fine provided you put it behind the meter. If you want to sell surplus electricity to somebody else that's the other side of the meter, then there are legislation challenges that you are actually forbidden from doing that by law unless you're a big enough supplier to become, certificated and get permission to do that. So a lot of the challenges around generating electricity and trading it are legislative and regulatory challenges rather than the technical ones. The idea of peer-to-peer trading is a very big one, where if you've got a surplus electricity yourself, you can sell it to somebody else. But in order for that to happen, you have to involve the distribution companies and so on and so forth. In terms of retrofit, have you got space for the batteries? Have you got space for the PV? I think it's those kind of challenges really, because the technology around PV and batteries is, I think a lot of the problems, a lot of the challenges have been solved. The problems come where you want to do other things and have more sophisticated systems.
That's great, thank you. We've had a few more questions come in. We've got another one from Maya Pal. What about the project economics? For any project to become mainstream, it has to be economic compared to conventional heating methods.
Yeah, well, I think that's absolutely the case. And one of the problems that we've got is that the energy markets distorted through, well, in all kinds of ways. I mean, I'm not either an advocate or a huge critic of nuclear energy, but government seems to pick up a big chunk of the cost of decommissioning nuclear power stations. In terms of PV and renewables and so on, there are some subsidies, feed-in tariffs and so on, and then there are obligations as well. So there are taxes, and really it's not a level playing field. One of the big problems that you've always got if you work in energy is that I think most of us as engineers and technologists are interested in the technical side of things, but you're not only trying to solve technical challenges, you're trying to do things which fit into the current network of subsidies and tariffs and so on and so forth. I mean, I absolutely agree that the economics of heat pumps are quite interesting. And whether a heat pump is actually cost effective or not depends on the analysis that you do and to what extent you take into account these subsidies and so on, and to what extent you don't. In terms of gas, maybe, there's an argument that says that gas should be more highly taxed or should be taxed because it, burning gas produces greenhouse gases, which have an effect. Now, in terms of other forms of pollution, then there is a principle that the polluter should pay. So maybe there's an argument for saying that gas companies should be taxed because burning gas produces pollution, but we don't seem to say that. So I think you're absolutely right. The economics are incredibly important, but the economics are distorted. I think it's an argument saying the economics are distorted, and maybe that's what we need to look at doing.
That's great, thank you. I've had two questions coming from Anne Hackinson. First of all, do you consider personalised local solutions, or do you look at the large systems like the 10,000 people systems or more? And one other question was a follow-up: is it possible to scale up the current systems that are in place?
Well, I mean, we can all do a little bit. So we can all go for personal solutions, but I think, as was implied by the previous question, Whether we do that or not is going to be constrained by the economics, and it's still a little bit. I mean, if you're talking about putting PV on your roof and having your own battery pack, in economic terms, if you look at the capital cost and the operational cost over the life cycle of the lifetime of the system, then the economics is a little bit marginal at best. You might decide that you want to do it for resilience. I mean, there are always predictions in the UK that the electricity system will not be able to cope next year. It's always next year, and we may be subject to power cuts. And, you know, I'm old enough to remember that during the 1970s, we were subject to power cuts. So maybe you have PV and a battery for your own kind of resilience. If we look at what's just happened with COVID, there was a fear, which thankfully didn't come about, that so many power workers might be struck by COVID that there would be a problem over keeping the power system running. Didn't happen, but, you know, a future pandemic may be worse, or there may be other future disasters. So you might do things in the small scale for yourself. But I think for efficiency, we really need to be looking at the bigger scale wherever we can. And the problem really is this bespoke nature of things. That you know, why have wind turbines become so successful? Well, we've optimized those about as far as we can go, and all you do now is you buy them and you stick them somewhere windy. Whereas with an integrated energy system, it's always going to be bespoke. You're always going to have to do different things depending on the area that you're in, and, you know, different combinations of energy resources and so on. So it's always going to be more complicated. But I think for ultimate efficiency, ultimate savings, then that's probably the way that you've got to go.
I think there was the second part of scaling up the current systems.
Oh, sorry, scaling up the current systems. I think that's kind of it's an interesting question, isn't it? And it's a bit like energy efficiency in buildings. That if you really want to produce energy efficient buildings, we just flatten the whole of a city and rebuild it, because retrofitting is always difficult. And there will be some potential for scaling up existing systems, but I think it's always going to be difficult.
We've got one more questions coming in. It's from Amadine and Zane. So thank you for a very interesting overview. To be able to power the future electrification, for example, heat pumps, electric vehicles, etc., we need to have huge deployments of REs and very large-scale energy storage, both electrical and heat. How can these two key requirements be met within the net zero framework?
Well, if I had the absolute answer to that, then I'd be a very rich man, I think.
Yeah.
I mean, energy storage is you know, electricity storage is particularly difficult, and the answer is we don't know. I mean, where you've got the potential, then hydro storage is really effective, but you need a mountain with a lake at the top of it, and there are all kinds of novel experimental schemes around pumping used coal mines full of compressed gas, and then when you need the energy, run that compressed gas through a turbine for generating electricity. Heat storage via stratified hot water tanks or phase change materials. There's a lot of potential there, and that's being done. That's possibly less challenging. There's a lot of interest in storing hot water in the subsoil, but again, solutions there are going to be bespoke. And an interesting point from what the questioner was saying was the zero energy framework. Let's not forget that we really need to be looking at the total life cycle costs of all of these technologies. And I mean, there's a huge potential problem coming up with PV, because we're putting PV everywhere. PV panels have a life of 20, 25 years, but what do we do with them afterwards? Because it's not very easy to recycle them. There's a big potential problem coming with PV and what we do with it. And there's also a problem with PV in as much as the production technology can be very polluting. So I think we do need to be looking at, you know, kind of full life cycle costs for all of these things. But as I say, if I had absolute, there's some indications, but if I had absolute answers, then I'd probably be rich, and I'm not. But interesting projects, and I'm interested to work in them.
That's great. I think that's all the questions that we've got in today, Bob. I want to thank you once again. Really appreciate your time.
Thank you very much.